Hello and welcome to Physical Attraction. This episode is on inertial confinement fusion and it's called Two-Faced Destroyers. Last episode we described how the invention of the laser gave scientists a new opportunity to pursue a totally different avenue towards nuclear fusion. To get nuclear fusion to release the energy that's locked up in those nuclei, you need to heat plasma to extraordinarily high temperatures and create a very high density of nuclei. That way, the nuclei will have enough energy to overcome their mutual electrostatic repulsion when they collide, and the temperature and density ensures that collisions will happen frequently enough and with enough energy to liberate more energy than you're supplying. In magnetic confinement fusion, the response of plasma to electromagnetic fields is used to attempt to contain the burning plasma for as long as possible. In a tokamak, the magnetic fields and the current that's driven through the plasma also help to compress and heat the plasma to hopefully obtain near fusion conditions while you continue to contain it. Inertial confinement fusion is more like detonating a tiny hydrogen bomb. Attempts to skillfully and dexterously hold the plasma as it burns are abandoned in favour of briefly attaining extremely high energies and densities in a controlled implosion. This idea, using a tiny pellet of fusion fuel that's rapidly compressed to release energy, is the mechanism behind the hydrogen bomb, which uses X-rays from a fission bomb primary to compress that capsule of fusionable material. Prior to the 1960s, scientists looked for and struggled to find a way to compress the secondary fusion capsule enough to release net energy, but without literally detonating an atomic bomb, which tends to ruin your power plant and the surrounding neighbourhood just a bit. When the laser was invented in the 1960s, scientists finally had that mechanism, something that could deliver a sizable quantity of energy to a very tiny place, the fusion fuel capsule. Lasers could produce pressures, due to photons bouncing off the capsule, of billions of atmospheres. Furthermore, lasers could produce very collimated, very spatially focused beams. To cause fusion to happen, you need almost perfect spherical symmetry in your compression. That's why the Teller-Ulam bomb device needed a special design to reflect the X-rays onto the fusion pellet so that they all arrived simultaneously. It was also partly why ideas like firing pellets into the capsule didn't work or using explosive shockwaves didn't seem to work, because getting them to simultaneously hit the capsule from all sides was very difficult. With lasers, where the timing and spatial frequency of the beam can be controlled exquisitely with mirrors, this became a real possibility. The first people to generate thermonuclear neutrons this way we covered last week. It was the private company KMS Fusion. We now know that their use of infrared lasers was never on track to produce net energy gains, but it sparked a great deal of interest for, and funding in, the field. And naturally, because inertial confinement fusion involved creating an incredibly powerful lasers, and studying how these lasers could be used to trigger a small-scale thermonuclear explosion, the centre of research for this dual-use technology became the United States of America. In fairness, they were part of the tokamak revolution too, but ultimately, the big explodey giant laser products that got an awful lot of funding for potential military applications were all in the USA. But the first major attempt by the US government to create this inertial confinement fusion was called Janus, and it was more or less a catastrophic failure. The neodymium silicon laser that they were using was simply too powerful for the optical equipment. The array of lenses and mirrors that they needed to focus the beams onto the hull-round fuel capsule would quickly heat, melt, and distort the optical system as the laser passed through them. Anyone who's ever been in a dark room fiddling around with laser beams for 10 hours in their undergraduate practicals, or even as a graduate student, will sympathise with the fact that a tiny defect or imperfection in an optical system can result in a very big impact on the result that you're trying to achieve. In the case of the Janus laser, these little defects, burns, or misshapen parts of optical kit resulted in hot and cold spots in the final beam. This would of course prevent the fuel capsule from being symmetrically illuminated, but of course this wasn't the worst of their problems. What started as a slightly hotter spot of the laser, a zone where a few more photons were impacting, could quickly become exaggerated as the laser beam passed through more and more mirrors, lenses, and other optical components. These hotspots could totally destroy optical equipment. So nearly every time the Janus laser was turned on, it would destroy some component of kit somewhere along the line, rendering the whole apparatus useless. These non-linear optical effects, as they're called, put paid to Janus, and they became so severe after just the first few amplification stages of early lasers that it was seen as essentially impossible to exceed the gigawatt level for inertial confinement fusion lasers without destroying the laser itself after just a few shots, which is a pretty big problem given how valuable the lasers are if you want to have a sustainable power plant. Even though the machine's laser pulses only released around 10 joules of energy a pop, around the energy you'd use to lift a bag of sugar a metre into the air, where of course it would then be used as an offensive weapon against unknown assailants. When you concentrate this small 10 joules onto small enough spots and in tiny amounts of time, it was more than enough to wreck the equipment. There's a picture of Janus from how it looked in 1975 that I'll put up on Twitter at PhysicsPod with this episode so you can see what it looked like. And it was an unwieldy beast. The next generation machine they used was called Argus. The plan here was to make the apparatus much, much larger. Janus could fit inside a fairly large room. In fact, it's not too dissimilar from many lab setups that I've seen. But Argus was more like the size of a sports hall. Why so large? Well, the beam lines for the lasers involved had to be very long. The purpose of all of the lenses and mirrors in the apparatus is to amplify the beam, shape it to your own desires, and focus it down on that capsule of fuel. The laser itself produces a great many coherent photons, but to focus them down to the size of the capsule and attain the concentrated power that's required for inertial confinement fusion to be feasible, this requires many amplification stages. By making the beamline longer, it was possible to add an extra spatial filtering stage after each amplification stage. These filtering stages were pretty simple. They essentially just involve passing the laser beam through an aperture the size of a pinhole after each amplification. That way, the hot and cold spots, the bits of laser that were misfiring or ending up in the wrong directions, were carefully filtered out. You can use the same thing as this on all kinds of different optical imaging as a way of getting rid of features you don't want. In this case, any imperfections in a carefully collimated beam. Now this technique had its downsides. Because you were filtering out a great deal of the power that was supplied to the laser in these filters, it meant that you needed a stronger laser to supply the same energy to the fuel capsule. But since the alternative was totally destroying the laser kit and apparatus, this was certainly preferable to that. Whenever you talk to someone who works on these big lasers, you'll understand that they're most keen to talk about the power of the laser. In terms of, well, power. Power is just the rate of an energy release, energy divided by time if you like. So you can get unlimited power, well, very high power, by releasing a huge amount of energy over a reasonable amount of time, or a reasonable amount of energy over a tiny amount of time. So it's technically true that this Argus laser operated at a stunning 4 terawatts of power way back in 1976. 4 terawatts, for context, is comparable to the entire world's capacity to generate electricity in 2018, which was around 6 terawatts. So yeah, saying that your laser operates with power equivalent to every power station in the world operating at maximum capacity sounds very impressive, and it gives you some good mad scientist street cred. But admitting that it only operates at this power for a matter of picoseconds, trillionths of a second, and hence is only releasing a few joules, or the amount of energy released when you drop a tomato on the ground, or, if you prefer, 1/60th of the energy you're constantly radiating away each second just by sitting still, suddenly it sounds a lot less like a giant death ray and a lot less impressive. So if a laser scientist ever quotes you the power of their laser as part of its specs, do ask them how long they can keep it up for. Laser braggadocio aside, the Argus laser was capable of producing bursts of fusion neutrons, like the Zeta experiment did for pinch magnetic confinement fusion before it. Argus was designed primarily to characterise these large laser beamlines and laser target interactions. There was not really a major attempt to actually achieve the ignition state in the device, as they thought that, at the time, the energies Argus was capable of delivering wouldn't be enough to get fusion capsules to ignition. So they just wanted to learn from the mistakes of experiments, where avoiding the errors that things like Zeta had come into, where scientists mistakenly thought they'd achieve fusion when they hadn't, because they didn't understand the plasma. So the main purpose of Argus is to develop techniques that would measure the implosion of the fusion capsule and how the laser interacted with the target. Even as a test device, it was performing well. But anyone who's been paying attention to the history of fusion over our saga so far will anticipate what happened next. The real problem with Argus, and the new biggest headache for inertial confinement fusion, was the dang electrons. The plan is to irradiate either the fusion target or a whole realm that surrounds it with intense light, the ultimate aim being to heat and compress the nuclei in the plasma. The problem is that when you shine those lasers directly onto matter, they heat up the electrons first. The light, densely charged electrons interact more strongly with the lasers than the slow, heavy, neutron-laden nuclei. These hot electrons buzz about and reduce the production of the hard X-rays that will compress the fusion reactor by colliding with each other and photons and drawing energy away from the nuclei. Worse still, they would generally get so hot that the target exploded before the nuclei had sufficient time to collide with each other and the photons and warm themselves up. Hot electrons and cold nuclei is no way to make fusion happen. It's just an incredibly efficient way to blow up a tiny capsule before it has chance to reach fusion conditions. And if the electrons are preferentially heated relative to the nuclei, you will blow up that tiny capsule far faster than you'll ignite a working fusion fuel. As with all fusion experiments, we shouldn't be too narrow-minded about whether they succeeded or failed. If fusion ever becomes commercially viable, all of these roadblocks that were hit along the way by various experiments will be seen as valuable discoveries on the road to finding something that worked. So Argus was successful at eliminating the problems of its predecessor with this new method of spatial filtering. Now they didn't need to worry about burning up parts of their apparatus. And it did allow the targets to be heated up to unprecedented temperatures. It also allowed them to develop X-ray diagnostic cameras that could view the hot plasma that was being produced in these targets. But of course, because of this hot electron problem, it wasn't capable of producing net energy. Future experiments would attempt to improve on the hot electron problem by changing the wavelength of the light. If you increase the frequency, and hence energy, the wavelength of the laser light decreases, and here you can hope to heat the ions slightly more preferentially than the electrons. They were able to do this by passing the laser through certain crystals that could double or triple the frequency of the beam. These crystals are called nonlinear optical media. They don't just refract the light like a normal crystal would, but instead, depending on the direction of the photon, it picks up a different phase shift. So it's almost analogous to water waves being forced to move at different frequencies, and then interfering with each other. The result can be a wave that's made up of a sum of the original frequency, plus doubled or tripled frequency light. Again, though, for those trying to design a practical inertial confinement fusion device, having these big non-linear crystals that were tripling the frequency to try and reduce the interactions with the electrons of the laser, well, just having more components added to the expense, added to the energy losses, which means you need a more powerful laser at the start of the thing, and it adds to the complexity of the beamline overall. Nevertheless, the results were promising enough that scientists at Lawrence Livermore Laboratory were constructing an even larger laser. For a cool $25 million in 1970s money, they produced a device with 20 separate beamlines, 20 separate arms of the laser that would irradiate a target from all different directions, with 30-metre long arrays of optical equipment, fed by a powerful laser. Nowadays, inertial confinement fusion scientists will tell you that this device, which they called Shiva, after the many-armed Hindu god, was also just a prototype, but it still wasn't known what conditions would be required to achieve ignition with inertial confinement fusion. Shiva would prove that any calculations that suggested this design could produce more energy than it required were wrong, by a factor of around 10,000. The problem was, you guessed it, a new kind of plasma instability that was discovered. Charles Safer has by far the best explanation of this in his book, The Sun in a Bottle, which you should all read, so I'm going to borrow part of that explanation here. Imagine filling a glass to the brim with water, and then tipping it upside down. The water falls out, right? You don't need a physics degree, or even an understanding of Newton's laws of gravity, to explain or predict that. Except that even this is a little bit more complicated than you might think. Atmospheric pressure arises due to particles from the atmosphere smashing into us from all directions. It's around 101,000 pascals, which means that every square metre of surface area has a force of 101,000 newtons pushing down on it due to that atmospheric pressure. That's equivalent to a weight of around 10,000 kilograms. Luckily, we are used to this balance of internal pressures and external pressures, and so we really don't feel the immense weight of the atmosphere most of the time, except maybe on Monday mornings. But this atmospheric pressure pushes in all directions. It's more than enough to keep the water in the glass when you turn the glass upside down. In fact, under certain circumstances, it will. If you fill a glass to the rim with water, hold a smooth piece of cardboard over that rim, and then tip the glass over. Please try this outside or over a sink. If you then carefully let go of the cardboard, you'll see that the water stays in the glass. The cardboard clearly isn't holding it back. That just wouldn't make sense. Instead, it's supported by air pressure. According to Safer's calculations, you'd need a glass of water 30 feet tall for the weight of the water to overcome the upward pushing atmospheric pressure. Which then raises a very serious question. If there's enough force to support a huge column of water pushing upwards on the water in glass, why does it fall outwards when you turn it upside down? You wouldn't have thought, why does water fall out of a glass when we flip it, would be a question that you'd need complex physics to answer. But it turns out that complex physics has a way of getting into all kinds of everyday situations that we didn't expect. The answer is something called the Rayleigh-Taylor instability, very familiar to those of us who've listened to tales of the instabilities that affect plasmas in the past. When you have a boundary between a dense and a less dense liquid, it's inherently an unstable situation. The liquids will want to trade places. A less dense fluid, air, is pushing on a denser fluid, water. If there are any slight imperfections or deviations along that surface, those bumps will get bigger and bigger over time, as water and air rush into the gaps between each other. Regardless of how careful you are, there will always be some imperfections that can grow rapidly. Soon enough, big tendrils of water will start forming, breaking off and falling down, and eventually the entire glass of water rains down in the familiar spattering, sputtering manner. After all, when you tip over a glass of water, you don't see a perfectly glass-shaped column of water fall down to the floor, do you? No, instead there's this instability, and if you watched it in slow motion, you'd see these tendrils form. The cardboard, though, is a solid. It's held together by stronger bonds than the fluid, and imperfections in the surface area aren't free to flow or grow. So air in contact with cardboard, or water in contact with cardboard, is a stable situation, in just the same way as the water can be kept in the glass. This you can handle, and so, if done carefully, you can keep deviations from forming at all, and there's no Rayleigh-Taylor instability. Trying to get laser confinement fusion to work is like trying to keep the water in the inverted glass, only without the cardboard. That's because you're attempting to compress the deuterium-tritium capsule with something that's less dense. Inevitably, before you even reach fusion conditions, the deuterium-tritium fuel will be far denser than whatever you're trying to use to compress it. Photons or the hot atoms from the hologram capsule that's collapsing to compress the fuel pellet. Since you're trying to compress a dense substance with one that's less dense, you get the exact same instabilities as you find in the glass of water when it's turned upside down. If there's the slightest imperfection, dent, divot or hole or whatever on the surface of that compressing fuel capsule, or if it forms as the capsule compresses, that perfectly round sphere of fuel that you want to build and collapse quickly becomes spiky, with long tendrils and fingers that extend outwards. This isn't what you want. You want a symmetrical collapse that nicely compresses and contains the plasma fuel at high densities and temperatures. Instead, what you get is Rayleigh-Taylor tendrils that allow the plasma to escape and cool before it reaches fusion conditions. To have any hope of achieving that, you need to have a uniformly heated target. No hot and cold spots, no areas of underdensity and overdensity that will form these tendrils and cause the fuel capsule to break apart before it can be compressed to fusion densities. But even though the Shiva device illuminated a tiny sphere of fusion fuel from 20 different directions, the compression still wasn't uniform enough to avoid hotspots where the lasers hit the pellet. This was why, after Shiva, much of the efforts focused on indirect drive, heating a capsule more or less uniformly which then collapses down onto the fuel pellet. But even this technique wasn't enough to overcome the Rayleigh-Taylor instabilities entirely. And, as in the case with magnetic confinement fusion, every new instability made the calculations worse for fusion scientists and engineers. Devices performed many times less well in practice than they would do in theory. Nevertheless, despite growing concerns around this Rayleigh-Taylor instability, the mood in the inertial confinement fusion community was optimistic, or at least this was what they projected to the public. Here's a press release from shortly after the Shiva laser began reporting experimental results in 1979. Quote, "In recent months, the 20-armed Shiva laser system at Lawrence Livermore has attained a significant milestone on the road to the development of a laser fusion reactor. The Livermore group has reported that with target pellets of classified design, Shiva has driven the deuterium-tritium fuel inside the pellets to between 50 and 100 times liquid density. With unclassified ablative targets, they report achieving 10 to 20 times liquid density. 100 times liquid density is only an order of magnitude short of the densities that will be needed to achieve scientific break-even. This goal, namely the release of as much fusion energy as the lasers deliver to the target, or the somewhat more modest goal of thermonuclear ignition, may well be achieved by NOVA, the next generation system at Livermore, on which construction began in May. Yes, that's right. It will come as no surprise that the solution was to build another, larger machine that would hopefully overcome the problems associated with the last generation of devices. All of this is to say that by the time the $200 million laser confinement fusion research facility called NOVA was being constructed, at the start of the 1980s, it was no longer the case that inertial confinement fusion was going to be this new dark horse, this bright idea that could circumvent all of the complexities of containing plasma in a tokamak with a quick, cheap device that could act like a tiny atomic bomb. Nor was it the case that the invention of lasers was new, exciting and fresh enough to make the technology easy to develop. Instead of a young, upstart field that took over from magnetic confinement fusion, inertial confinement fusion followed a very similar trajectory. Initial optimism followed by failures and the discovery of instabilities, followed by renewed but more cautious efforts with ever larger and ever more complex machines. Individual scientists would always, of course, have their own reasons for preferring one method over the other. ICF was always more popular in the United States than anywhere else, in part because of the large amounts of military funding it could often secure due to the dual-use nature and weapons potential for those vast lasers and controlled explosions, compared to tokamaks, which are far more difficult to weaponize in the same way. From here on out, though, the two trajectories of fusion would evolve in parallel. Two efforts with two quite different central ideas for achieving fusion, but ultimately, so far, with somewhat similar results. Next time, we'll take fusion science through the decade of good pop music and awful fashion, the 1980s. It was a decade that would culminate in one of the greatest academic scandals and hysterias in the history of physics, and one that still haunts fusion scientists to this day. All due to a failed experiment by two electrochemists called Pons and Fleischmann. You've been listening to Physical Attraction. You can find everything you want to know about us on the website at www.physicspodcast.com, where you'll also find a contact form that goes to my email, which you can send any comments, questions, concerns, issues you'd like to raise, and I will bring them up at the end of the next episode or at the start, whatever makes sense. You can also donate to the show there, PayPal, Patreon. These are ways that you can get the bonus episodes that we've recorded in exchange for a modest fee that helps us support the show and carry hosting costs. Until next time then, take care of each other.